Hello everyone. Today we're talking about predictions and modeling. Here's an overview. We're ready to start. This is the last lesson before ANOVA. In this unit, we've already talked about hypothesis testing from one sample. We've talked about two sample test chi-squared tests. We've also talked about correlation. Now we're going to use what we know about correlation to be able to talk about regression and prediction, or modeling and prediction. Okay, the goals of this lesson are to review the equation of a line and to find the line of best fit and its properties, so the line of best fit for data. Then we're going to use the line of best fit to make predictions. Let's start with the equation for a line, y equals mx plus b. This m is the slope of the line. This b is the intercept. The graph of the line is the set of all points that satisfy this equation, okay? The set of all points that make that equation true. So, for example, if we have y equals 2x minus 3, if I plug in x equals 0, what do I get for y? Y equals 2 times 0 is 0, minus 3 is negative 3. That's my starting point. My intercept, which is where the graph intercepts the y-axis. Well, where do I go from there? My slope is going to tell me. If my x increases by 1, my y value is going to increase by m. If we have x plus 1, my y is going to be increased by m. Since my m is 2 here, I'm going to increase by 2. Another way to think about this is that m equals the rise, or the change in y, over run. So that's change in y over change in x. In our example, 2 is the same as 2 over 1. So that rises 2, as it runs 1. And so there's my line. Okay, so you'll recall that before we're working with a scatter plot, and when a correlation is suspected, we would like to try and predict one of the variables, the response variable, given the predictor variable. Correlation means one variable gives information about the other. This is called prediction or estimation. We use what's called the line of best fit, which is also as we'll see more of, we'll see this is the least squares regression line. And it's the equation of a line. So here's my slope. B1 is my slope. B0. The slope of the regression line is r times the standard deviation of y. Goodbye. And that's your B1. Once you have B1, you compute the mean of y and the mean of your x variables. And once you do that, you can then form your intercept, which is B0. Once you have that line and some data, you use this line, plug in x tilde for x, and you get out y hat. That hat is the notation we use for something that is estimated. And the tilde is sometimes used to represent data. So you might not have data for y, but if you have data for x, you can determine what y is likely to be. If no correlation, r is basically 0. B1 is basically 0, and B0 is y hat, the average of y. Your best prediction of y for any x is B0, which equals y bar. So the best approximation of y is the mean of y when no information from x can be obtained. No correlation means no information from x. If there is a correlation, you will have some slope, either positive or negative, and that slope is B1, or r times the quotient of the standard deviations. You can take that line, you can plot it, and it's always going to go right through the middle of your data, like this line does. It goes right through there. And so when we are using the line of best fit to estimate a y value, it's always going to land right on that line. So, for instance, if I had somebody that was 42 pounds, their y value, their height, is going to be somewhere over here, like 82 inches. given the data, that's our best guess of their height, given that they weighed 242 pounds. So this here is going to be my y hat. This here would be my x tilde. And that's how I approximate. Now, there's something called the residual plot. Those are the errors. For all of the data, we have a y, and we also have a predicted value, which is this value on the line of best fit. So for instance, let's take this data point. That's an actual data point, and it differs from the prediction, which is down here on the line of best fit. This difference is the error of our prediction. We're always going to have some predictive error because our data is generally noisy or depends on things other than what the x value is. This error is also known as the residual. Residuals can be plotted. This plot is a plot of the residuals of our height and weight linear fit, our line of best fit. These 2 points correspond to these 2 points. The reason one is lower is because my line is sloped. The difference between this line and this line is smaller. On this plot, I am plotting the vertical distance. This point is below the line of best fit, so on our residual plot, it's negative. These 2 points are represented in my residual plot. The formula I gave for the line of best fit satisfies the least squares property. What does that mean? If you take the residuals and you were to make a square, so you have this data, right? And you have your line of best fit, and your residual is the difference between your data and the line of best fit. Well, if you take that difference and you square it for every single point, you're going to get a bunch of squares. If you find the area of those squares together, the line I gave you will minimize that quantity. Suppose we wanted this line here to be a line of best fit. Is this a line of best fit? Well, no, because look at how big these residuals are. If you square the residuals, these would all be very big. That is a bad choice of the line of best fit. It does not satisfy the least squares property. But our line of best fit is guaranteed to satisfy the least squares property. Our line of best fit that I just gave you from above is guaranteed to satisfy the least squares property, meaning it is the line that has the smallest sum of these residual squares here. And so that's a good way to find a line that goes right through the middle in an optimal way. Okay, let's think about the interpretation of r squared. So we observe that our prediction is b1x times b0. If we compute the mean of y, or the mean of y hat, that is going to equal, if I take the sum of all my y hats, divide them by n, that's going to be the same thing as b1. I can factor out of my sum, and these constants here are just going to add up. I'm going to have n of those b0s, but I'm dividing by n, and so I end up getting b1 times mu x plus b0. Or if I were to find the standard deviation of y hat squared, that is going to be the sum of y hat squared is mu of y hat. And mu is a little bit of abusive notation because it is a form of data. We should do y hat bar, but I don't want to do y hat bar, so I'm just going to use mu. And so what this comes out to is my b0s cancel, and I can factor out my b1, and I end up getting just b1 squared. It's squared because I'm squaring everything, times sx squared. And so that's how we get that equation. Remember, b1 equals r times sy over sx. b1 squared is r squared sy squared over x squared. If I multiply by sx squared, I just get r squared s squared y. So the variance predicted by the x variable, so this right here, if there's any variation, it's from the x variable. Y hat is determined by x. Y hat represents the variance predicted by the x variable. R squared is less than 1, so it's some proportion of the variance of y. Is that the variance predicted by the x variable is a full x squared of the actual variance of the y variable. There's some noise or variance unique to y, but the proportion of that variation of y explained by x is r squared. That tells you how much of that variation in y can be contributed to the variation in x. Okay, now, there's two different ways you can fill in values when you have a line of best fit. One, you can do interpolation, and that's when you have your data and your line of best fit. You're curious about a particular value inside of the range where your data is. See, so the range of data is like here, I've got x values. That's called interpolation. Using the linear model to predict y values inside known data points. Extrapolation is using the linear model to predict values outside known data points. So that would be using this linear approximation to approximate this blue point here. So I have a x value that I want to find the y value of, and so I plug it into my linear model, and I get some y value out here. This is called extrapolation because I am doing it outside of the data that I have. That is a risky process because you don't know how far after your data these x values are going to follow this linear regression line, or if they even make sense. Generally, linear correlate may not last long. It may only apply to the data, a range. Here's some examples of where that might be problematic. Sometimes extrapolation is good, but it needs care. Let's take an example and use our regression line to predict the stopping time for a car going 21 miles per hour. So we're going to use the same data that we did before, data from the 1920s about the car stopping time. Okay, I have my sheet from day 22. We're just going to add to it. So first thing I'm going to do is I'm going to get my line of best fit. We have a statistically significant linear correlation. And so the next thing to do would be to plot the line of best fit. We start with B, and that is just going to equal, well, I need a few things here. I'm going to need R, S, and XY, SY. R is our correlation, so I'm going to retype that in. Get my first array here, and my second array there. Good. So there's my two arrays. Enter. There's my R, and that matches the same R I found before, right there. Okay, now I need SX and XY. I'm going to do equals stdev.s, select this, down to there, enter. There's my standard deviation for my x variables, or my explanatory variable. Then I'm going to find the standard deviation for my response variable, stdev.s. All right, there we go. And so B1 is going to equal R times SY divided by SX. How do I know it's SY over SX? Think about slope. Change in Y over change in X. Press enter. There's my slope for the line of best fit. Now I would like to find my intercept, B0. To do that, I need B1, which I already have, but I also need X bar and Y bar. So right now, I'm going to take the mean of my data. So this thing's going to equal average There I take the mean of the speeds, and then I take the average of the stopping times. And so now B naught is going to equal y bar minus B1 times x bar. Enter. And there's my intercept. Let's come up with my model and predictions. I'm going to call this stopping distance. This is going to be my predicted distance. That is going to equal B1 times the speed plus the intercept, B naught. And I'm going to fill down, so I want to put some dollar signs there. Enter. Now I'm going to go ahead and fill it down. Okay, now I want to plot these. I can increase the plot area. I selected my plot. I saw the data being used is highlighted. I dragged the right side dot to include my predicted dists. And when like that, it automatically made it orange. And I look at my scatter plot, and there is the predicted. The predicteds are the orange points. That's my line of best fit. Now, the question wants me to predict the stopping distance associated with 21 miles per hour. I'm going to put this point in here, 21. Oops, sorry. Put that right here, 21. And then I'm just going to drag this, or copy, paste that value. Notice what it's doing. It's doing exactly what I need it to. It's going to take my B1 and multiply it by the 21, which is in the red square, the red cell. And then it's going to add my intercept. And so that gives me my predicted distance. That's how far it's going to go before it comes to a complete stop. 65. Okay. And so that would be my answer. Another way of writing this would be to report the B1 and the B naught. So I have taken a screenshot. I have my B1 and my B naught. Copy and delete, paste. So there's the information for my line of best fit. I've got y hat equals 3.9324 times x, which is my speed, minus 17.6. We have 65 is about 3.9 times 2 minus 17.6. That's from Excel. If x is below a certain value, then your stopping distance is going to be negative. Well, that doesn't make sense. So this has a limited range of usefulness. So if x was more than 5, if x were less than 4, this would not make sense. If you were going 4 miles an hour, it doesn't make sense. This model is not valid. It's valid within the range that it was designed for. So it's valid within the range it's designed for, but clearly not valid outside of that range. This 21 here is interpolating within the range of x values. Let's go back to Neptune and burglaries. Does there appear to be any correlation between the data? And there appears to be a statistical correlation between the data. So find the linear model relating the distance the Earth is from Neptune and the rate of burglaries. So the x value, the explanatory variable, is usually the first one, and the response variable is usually the second one. About what burglary rate would you expect in 2020 Neptune is the input variable, or the explanatory variable. So this will be my x. So that looks good for B1. My regression, I've got to fix this range right here. Let me get this range up here. Distance from Neptune to 45. Look at that, 8 to 45. I'm going to do that. C8 to C45. All right, enter. There's my correlation, same as before. Now for this one, the x's are B8 to 45, B8 to B45, and this one, this one's going to be C8 to C45. It doesn't like my asterisks. 8. Okay, good. Now this one, that looks okay. We're just missing these. This one needs to go to B, to B45. Doesn't have to be capital. And then this one is going to be C8 to C45. Enter. All right, let's take a look. This is going to be my predicted burglaries, and it is going to equal my slope. Look at that slope, 2,008. That means for each unit of distance, burglaries increase by 2,808 per 100, whatever that rate is. I've got my slope times the distance plus B naught. I'm going to put in my dollar signs now. Hold those the same. Oopsies. Okay. All right, let's see what happened. That looks good. Oh, look at B. I want this to be F. Okay, F. All right. Let me make sure it's referencing the right cells. Yeah, that looks good, and the dollar signs are in place. I'm going to fill down. There it is. Very good. Now for the real test, I'm going to click on my plot and drag my data. Okay, okay, click on my plot. All right, it doesn't seem to be working. So I'm going to delete my plot, select all of this data, and I'm just really going to hope that it's going to put the distances as the x values and those other two columns as the y values. Insert chart, scatter plot. Looks like I got lucky and Excel did exactly what I wanted. This rarely happens, but it happened today. You can see the orange ones are a good approximation of the blue ones. Now, what was asked of us? We were to find what distance I would expect when Neptune is 29.9034 astronomical units away. 29.9034, I think it was. All right, and then copy, Command C, copy this formula, Command V. There it is. Let me look. Yep, referencing the right stuff. And so my value there. Now I wonder if I can extend this. I wonder what happens if I go like that. That point right there, this point here, is my new point. It doesn't have a blue point associated with it. This is extrapolating. I've extrapolated beyond the range of data. All right, okay, let's go ahead and do the same thing we did before. Grab this information with a screenshot. Let's just take this whole thing. Let's take line of best fit. Let's take that whole plot as well. Done. Copy and delete. Go back to Notability. Throw that right there. All right, my data, my line of best fit is going to be y hat, predicted distance, burglaries, is going to equal 2,800.6353. Let's go 4 decimal places because I think astronomical units was 4 decimal places. Now this is being multiplied by y. So what are the units? How many decimal places is the data for y? Let's take a look. Go to Excel. Y is to the nearest 10th. So if y is to the nearest 10th, then we'll make this to the nearest 10th as well. About like that. Times x is... Okay. That is my line of best fit. When x equals 29.9035, I found that y, my predicted number of burglaries, is 315. Let's check that number again. Yep, 0.4 burglaries. That's number 8. Okay, what did we do today? We talked about the line of best fit. We talked about an interpretation. We talked about linear model. We talked about an interpretation for r squared, interpolation, and extract. Going back to this example, we see some variation in what x equals, and we'll talk about the variation in class. And that's it. Have a wonderful day, and we'll see you later. Thank you.